A single LED light bulb may cost only a few dollars, but with more than 15 billion units produced every year, they have built an industry worth over $100 billion, illuminating nearly every corner of the planet. The journey begins with a semiconductor chip, smaller than a speck of dust, passing through assembly stages, measured down to the micrometer, gold wire bonding thinner than a human hair, color conversion, protective encapsulation, and large-scale light testing before becoming a source of illumination for the entire world. And today, the Factorin takes you deep inside that process, where chips that are almost invisible are transformed into billions of light sources that brighten the planet every single day. The birth of LED light. For more than a century, humanity accepted a costly trade-off, burning vast amounts of energy just to produce a small amount of light. From Edison's incandescent bulbs glowing with intense heat to fluorescent lamps filled with toxic mercury, the world longed for a light source that was cleaner, cooler, and far more durable. It was within this demand for change that LED technology was born. Yet, in its early days, LED was simply not powerful enough. For decades, it remained confined to a supporting role, appearing only as faint, red indicator lights on control panels, while incandescent and fluorescent lighting continued to dominate. But that very limitation posed a defining challenge. If a blue LED could be created, everything would change. In 1994, Japanese engineer Shuji Nakamura discovered a suitable semiconductor material that allowed blue LEDs to emit light reliably for the first time. This breakthrough made white light possible and marked the beginning of a new era in human illumination. Crystal growth. Every LED lamp begins with a semiconductor chip, and to create that chip, factories must start with crystalline substrates, most commonly sapphire. But before any crystal can be processed, human beings must enter an environment that is almost absolutely clean. The entire chip manufacturing area operates as a massive clean room, where a single microscopic particle of dust can be enough to ruin thousands of chips at once. Engineers and technicians are required to change into full protective gear, one-piece cleanroom suits, hoods, masks, and gloves, and anti-static footwear, before passing through high-pressure air showers designed to strip away any remaining dust or contaminants. Once conditions meet the strict specifications, the sapphire substrates are loaded into epitaxial reaction chambers operating at extremely high temperatures. Gases containing gallium and nitrogen are then introduced, flowing across the sapphire surface and bonding atom by atom, crystallizing into ultra-thin layers far beyond the limits of human vision. Through this process, specialized semiconductor layers are formed and stacked with precise order, creating a p-n junction structure. It is within this junction that, when an electric current flows, charged particles collide and release energy in the form of light. This is the moment LED light is born at the atomic scale. Creating the LED circuits. After epitaxial growth, the wafer appears smooth and mirror-like to the naked eye, but in reality, its surface already contains millions of semiconductor structures that are not yet capable of producing light. To transform these structures into functional LED chips, the wafer must undergo the process of photolithography. Inside a controlled yellow light environment, the wafer surface is coated with a light-sensitive material known as photoresist. Ultraviolet light is then projected through a precision mask, drawing microscopic patterns onto the wafer with accuracy down to individual micrometers. The unwanted regions are washed away, leaving behind an intricate network of ultra-fine circuit features. Next, the wafer is transferred into a vacuum chamber, where an extremely thin layer of metal is deposited to form the electrical contacts. At this stage, the entire wafer has effectively become a massive light circuit board, containing tens of thousands of individual LED chips, all formed simultaneously and waiting to be separated in the next stage of production. Wafer dicing. When the entire microcircuit structure has been fully formed across the surface of the wafer, the journey of light enters a decisive stage, chip separation. Beneath its mirror-smooth appearance, the wafer is in fact a microscopic map containing tens of thousands of identical LED chips arranged in perfect geometric order. The factory employs a high-energy laser system with extremely precise beam focus, guided along pre-calculated scribe lines. Between each chip, the laser cleanly slices the wafer into thousands of tiny square dies, minimizing cracking and residual stress that could otherwise damage the internal structures. Each individual LED chip, once separated, measures only a few tenths of a millimeter across, smaller than the tip of a needle. Yet inside, it contains a complete light-emitting region, semiconductor layers, and a fully formed p-n junction. At this scale, even a microscopic fracture is enough to render a chip non-functional. Immediately after cutting, the LED chips pass through an automated inspection system. Each chip is briefly powered on to verify that it emits the correct color and operates at the proper voltage. Defective chips are removed on the spot. Only those that meet all specifications are allowed to continue their journey to the next stage. After the wafer has been cut into thousands of tiny LED chips, all of them still remain firmly attached to a thin carrier film. In this state, robotic systems cannot pick up individual chips with micrometer level accuracy. For that reason, the film is fed into a crystal expander machine. Uniform tension is applied from all four directions, stretching the film outward. As the film expands, the chips gradually separate from one another, increasing the spacing between them according to pre-calculated dimensions. The result is a perfectly ordered chip grid, where every die is evenly spaced and precisely aligned. Once the expansion process is complete, the film carrying the evenly separated chips is transferred to an automated pick-and-place system, ready to enter the die bonding stage. Die bonding. Each microscopic LED chip is fixed onto a metal lead frame consisting of two terminals, the positive anode and the negative cathode. An automated die bonding machine dispenses a precisely controlled dot of thermally conductive adhesive onto a designated position on the lead frame. This adhesive plays a dual role. It securely anchors the chip in place while also providing an efficient path for heat dissipation. As a result, both the volume of adhesive and its placement must be accurate down to individual micrometers. The expanded film carrying the separated chips is fed into the machine. Industrial vision cameras scan the entire surface automatically, identifying the exact coordinates of each chip as well as the metal pads on the lead frame. This allows the system to calculate positional offsets within just a few micrometers, ensuring that every chip is placed with extreme precision. The robotic arm operates at near instantaneous speed: pick up, rotate, align, and place, each cycle taking fractions of a millisecond. A gentle downward force is applied to spread the adhesive evenly, preventing air bubbles and ensuring the chip remains perfectly level. Precision at this stage is critical. A misalignment of just 20 to 30 micrometers can cause color shift, reduce the LED's lifespan, or even lead to immediate failure in the next processing step. For this reason, once an entire strip of chips has been placed, the lead frames are transferred into a thermal curing oven. There, a stable temperature is maintained for minutes, allowing the adhesive to fully cure and permanently lock each chip into position as a unified structure. Precision wire bonding. After the LED chip has been fully secured onto the metal lead frame, the LED tray is transferred to an automated wire bonding machine. A spool of 99% pure gold wire with a diameter of 18 to 25 micrometers, 3 to 5 times thinner than a human hair, is fed into the system. High-resolution industrial cameras scan each individual chip and its corresponding lead terminals, calculating their exact positions with accuracy down to just a few micrometers. Using a combination of heat and ultrasonic energy, the machine forms a tiny gold ball at the tip of the wire. This ball is pressed onto the chip's electrode, creating the first bond. Immediately afterward,
the wire is drawn into a carefully shaped arc and lowered onto the metal lead to form the second bond. Then, the wire is cut and the machine moves on to the next chip. This process operates at extremely high speed, yet each step must maintain uncompromising precision. Each gold wire loop is tightly controlled in terms of loop height, adhesion strength, and tensile force to ensure reliable electrical connection and long-term stability. Once wire bonding is complete, technicians inspect every bond under high magnification microscopes. Each LED showing weak or imperfect bonds is removed immediately, ensuring that only fully qualified components proceed to the next stage. After wire bonding, the LED tray is transferred to the phosphor coating and epoxy encapsulation stage.
After gold wire bonding and initial inspection are completed, the LED frames are transferred to the phosphor coating area. Raw phosphor powder is first weighed using an analytical balance with an accuracy of 1/10,000th of a gram, equivalent to approximately 0.0015 grains. Depending on the target color temperature, engineers blend multiple phosphor powders, yellow, orange, pink, and other spectral modifiers according to precisely calculated ratios. After weighing, the mixture is sent to a high-speed mixer, where the phosphor powder is evenly dispersed throughout the epoxy solution. Next, the phosphorus epoxy mixture is loaded into the dispensing cylinder of a phosphor dotting machine. Thousands of LEDs mounted on LED frames are fed into the machine chamber, where ultrafine dispensing needles deposit an extremely consistent volume of the mixture onto each individual LED chip, accurate down to millionths of a liter, or approximately 0.000003 fluid ounces. This thin coating is responsible for converting the chip's native blue light into the white or amber light visible to the human eye. Once weighed, the phosphor mixture is transferred into a high-speed rotary mixer, where it is evenly dispersed within a liquid epoxy resin to form a uniform coating compound. Once coating is complete, the entire tray of LEDs is placed into a curing oven, operating at approximately 302 degrees Fahrenheit. At this controlled temperature, the epoxy fully hardens, permanently locking the phosphor layer in place and creating a uniform optical surface across all LEDs in the batch. The most fascinating detail is this: no semiconductor chip naturally emits white light. In reality, LED chips always produce blue light. It is the yellow phosphor layer that transforms that blue emission into the white light we perceive. This conversion process is the hidden secret behind modern LED color technology. Once the LED chips and gold wires are securely fixed in place, the entire lead frame strip is transferred into the epoxy molding area, the stage where the LED's signature transparent lens is formed. Liquid epoxy resin is injected into steel molds containing hundreds of precisely shaped cavities, designed to create standard LED forms such as 5mm round heads, flat tops, or oval lenses. The filled molds are then moved into a circulating thermal oven, operating at approximately 248 to 302 degrees Fahrenheit. Under this carefully controlled heat, the epoxy undergoes molecular cross-linking, gradually transforming from a viscous liquid into a solid, crystal-clear structure. When the curing process is complete, the LEDs are released from the mold in their final form, a rigid, transparent plastic lens, encapsulating the semiconductor chip and gold bonding wires, with the metal leads extending cleanly from the base. Final separation. Once the epoxy has fully cured, the steel mold is opened, revealing a long LED strip containing hundreds of individual lamps, appearing nearly finished, yet all still connected together on a single metal lead frame. At this stage, the product is still only a semi-finished component. Before moving on to separation, operators perform a quick visual inspection of each strip to ensure there are no molding defects. The LED strip is then fed into a deframing machine. Inside, a system of precision-aligned cutting blades and metal punching mechanisms operates with extremely high accuracy. In just a matter of seconds, the thin tie bars linking the LEDs are cleanly cut, releasing each LED package as an individual unit, precisely formed to its standard dimensions. Quality control to distribution. After being separated from the metal frame, each individual LED is fed into an automated electro-optical testing system. In a brief instant, the LED is powered on and illuminated, allowing industrial cameras and optical sensors to precisely measure brightness, color output, operating voltage, and color temperature, subtle deviations that the human eye cannot detect. At this very stage, the binning system begins its operation. Based on the collected measurement data, each LED is sorted into distinct groups according to brightness level, color characteristics, and electrical voltage. Pneumatic mechanisms rapidly direct every LED into its corresponding compartment, ensuring that when these LEDs are later assembled together on the same light strip or lighting panel, they emit uniform light without color shifts or brightness inconsistencies. From here, the qualified LEDs move on to the lead forming and wire handling stage, where their leads are shaped, aligned, and secured onto specialized conveyor systems, preparing them for the final steps of packaging or downstream assembly within the production line. Only LEDs that pass all inspections move on to final packaging. They are carefully dried and sealed in moisture-resistant bags or trays, labeled with binning data, batch codes, and production dates. The finished shipments are then secured and transported worldwide to factories producing LED strips, displays, toys, and electronic devices, ready for final assembly and delivery to consumers. Conclusion. Today, LED lighting has become an indispensable part of modern life. If you want to continue exploring similar journeys where familiar materials are created through precise and meticulously engineered manufacturing processes, follow the channel to take a closer look at how the industrial world operates down to the smallest details.